We get, finally, to the third video of our trilogy about the p-value to shed light on it. The first thing we did was to ask ChatGPT, why do we keep misusing the p-value? Curious. It seems that the AI has watched our videos. Let's look at this familiar table, is a linear regression model between PISA 2003 results and classroom size. What's going on? Why do all these numbers disappear? Unfortunately, the analysis of a statistical model in practice has become this. We no longer even look at the p-value, but the number of asterisks to determine whether or not the variable is significant, although we do not know very well what that means. And if it is usual to say that a variable is significant through this unjustified way of working, we'll call it the science of asterisks. However, more and more scientists are arguing about the p-value, and the complete way of thinking around it has been created to validate statistical results. They have been published in the best scientific journals, with a high impact on how the usual practice of inference is being approached in data science.
I think it's safe to say that more than 99.9% of science is not good. Yeah?
Entiendo que estamos hablando de que posiblemente dentro de muchos años descubramos que todo aquello que hemos hecho incorrectamente no serviría para nada, desde luego. Ahora, lo que se haga correctamente, por supuesto que servirá. Entonces hay que hacer las cosas bien, sencillamente.
And maybe in 50 years from now, we have to be patient. Then scientists will follow more the principles of science as they should.
We return to the PISA data. If you remember, in this graph, in general, we saw that it didn't seem that the class size had a big effect on the grade. The regression points out, however, that the coefficient is very significant, which is said to allude to the fact that it appears with 3 asterisks. But the scientists we've asked don't look at the p-value.
That's solved by the effect size.
The size and an effect or the importance of a result.
But the effect, if we are going to find it,
there was an effect where there was no effect.
How much that drug reduced mortality?
¿Cuánta es la diferencia para que tú en realidad puedas usar ese experimento?
If a treatment is effective or if it is meaningful.
And the size of the effect can be seen here is the value of the coefficient that we have estimated. In this case, it indicates that for each additional student in the classroom, the score will decrease, approximately by 1.76 points. Now, is that a lot or a little? Here begins one of the most important tasks of the data scientist. Although, beware, we do not always have a clear and direct answer.
Bien, deja que el lector saque sus propias conclusiones. A veces el investigador adopta un papel especialmente dogmático, ¿no? Como te voy a decir yo cuál es la verdad, no, deja que el lector lo concluya, ¿no?
For the reader to draw her conclusions, we must go beyond a table with asterisks. Consider, for example, the variable size that is associated with the coefficient minus 1.76. The first thing we must analyze is, how does the size variable vary? How much can a classroom increase or decrease? According to the descriptive statistics, the first quartile stands at 15 students per classroom. The median value is 25, while the third quartile is 35 students. Well, now let's use the model to predict the grade we would get if we went from a small class to a larger one. The difference is 35 points. The median value of the grade is 492 points. The cutoff is around 7%. Is then a relevant effect passing from a 35-student class to 1? Of 15 increasing the grade by 7%? Does it compensate for the changes that must be made in the school? Would it be profitable? Is it, then, significant? We leave this to you to think about. But as you can see, it goes beyond the 3 asterisks that the effect showed before. Where can we find a measure of the uncertainty with which we have estimated the coefficient? Indeed, here, in the standard error column, it is a good measure of the uncertainty associated with the estimation of the parameter. And it even appears on book covers. The intuition is quite clear. We will have more uncertainty the bigger errors the model has, or the more correlated the predictors are, what is called collinearity. We then will have less uncertainty the more the explanatory variable varies, or the larger the sample size is.
Cuando el número de observaciones es muy grande, ese es el efecto que predomina en la determinación de la varianza, con lo cual la varianza es reducidísima. Entonces, por ejemplo, si uno contrasta una hipótesis de beta igual a 0, es decir, estoy contrastando, la hipótesis nula es esta variable no aporta información para explicar este fenómeno. Si esa es la hipótesis que estás contrastando con una base de datos muy grande, hay un sesgo, no sesgo estadístico exactamente, pero hay una tendencia a que rechaces esa hipótesis.
Look at the confidence intervals of the parameter. They're quite narrow, and they barely move when confidence changes. Here, we work in a context in which it does not seem useful to do a test, since it would be easy to reject almost any null hypothesis that you propose. We grasp more information using the size of the effect. Information, by the way, contradictory to the statistical test, which had 3 asterisks, do not forget, and favorable to the sample evidence, which told us that there was not, in general, a very pronounced effect between the size of the classroom and the grade obtained. But just the opposite can happen to us. We estimate with a lot of uncertainty, that is, with low accuracy. In that case, the standard errors of the parameters are large, relatively, and lead us to wider confidence intervals for the parameters, where a bunch of different null hypotheses wouldn't be rejected. Our test, we say, has low power.
El problema es que de la misma manera que no rechazas la hipótesis en la que aparentemente estás interesado en contrastar, no rechazarías casi ninguna otra hipótesis estés o no interesado en contrastar. Es decir, tu contraste ha perdido mucha potencia. Tanta más potencia cuanta menos precisión haya tenido tu estimación.
So, again, does it compensate you to do a test knowing in advance that you are not going to reject a lot of hypotheses?
Contrasta una hipótesis paramétrica y no rechazándola concluye que he demostrado, dicen muchas veces, determinada hipótesis es cierta. Nunca se demuestra que una hipótesis es cierta y desde luego no porque no rechaces la hipótesis has demostrado que es cierta. Si no rechazas la hipótesis, lo que todo estadístico riguroso sugeriría es que inmediatamente construyas la función de potencia del contraste que has realizado, porque es posible que descubras que igual que no has rechazado esa, no rechazarías ninguna otra, incluso algunas muy disparatadas.
This article has caught our attention because it proposes to use a function, the so-called p-value function, to illustrate, in a simple way, this fact of being in a low-power context. The p-value function, for which the authors have created a package in R, allows you to see in a graph the p-values associated with a bunch of different null hypotheses. For example, here, we wouldn't reject all the hypotheses we have rounded up. If we increase the level of significance, we reduce the number of hypotheses that we would not reject.
It's a good graphical tool to aid such discussions. However, from whichever angle you look at it, you will conclude that this clinically significant reduction is more compatible with the data than to say that there is no effect.
He is telling us about an experiment they discuss in their article about Parkinson's sufferers who underwent an exercise program. The parameter of interest is the ratio of patients who had falls after doing the program, compared to the control group. The null that they test is if this ratio is 1, that is, that the treated fall in the same proportion as no treated people. They fail to reject the null with a p-value close to 20%. Well, as we can see, at 5% significance, we wouldn't reject a lot of very different null hypotheses, even one that would say that the treatment is successful because it would refer to a reduction in the rate of falls of more than 40%.
No te permite pronunciarte con suficiente precisión sobre aquella pregunta que diseñaste inicialmente. Lo siento, pero no puedo hacerlo.
Let's say it's irrational to speak of no effect, that this study showed that there is no effect. I think this is not warranted, and I think that the p-value function makes this quite obvious.
Esto a veces a alguien le puede frustrar, y entonces no he probado nada. No, bastante harás con decirle al personal que te está leyendo que mucho cuidado con concluir hipótesis contundentes después de un análisis empírico en relación con aquella pregunta.
By the way, what we have seen here applies to any model and methodology that leads you to use hypothesis testing to answer your question. You should think twice.
More or less, do the best you can in your analysis. I try to do the best that I can. And then be honest and describe what, as you say, the observed effect, describe uncertainty, and speculate about reason for your results. But I really try not to make this strong statement anymore.
In that spirit, we present the analysis we have on the question at hand. We have estimated a more complete model since, if you remember, we wanted to discuss the importance of classroom size between big and small cities. Our results are shown in this table. They're the predictions of the model in students, with different characteristics regarding where the school is, social status, and classroom size. Here we show classrooms of 15, 20, 25, 30, and 35 students. High, medium, and low social status, as well as big city and small town. The first thing we see is that in the low social status, represented in the blue columns, and in a big city, the grade varies by 15 points. However, it varies by 37 points in a small city, going from a classroom of 15 students to one of 35. In high social statuses, marked in red, there are hardly any differences. But it shows a slight effect in small towns. In the middle status, as we see, in big cities, the size of the classroom has no influence, since the grade barely moves. However, in small cities, there is a greater variation in the grade, 31 points. Finally, look at the difference between a classroom of 35 students from a big lower-class city and the same upper-class one, 167 points.
No confundas la significación estadística del coeficiente con el contenido informativo de la variable que le acompaña, porque estás hablando de dos entes que son diferentes. Una cosa es una variable potencialmente explicativa y otra cosa es un coeficiente estimado.
This table can help decision makers to think about the practical importance of the classroom size effect, depending on where the school is located. Is it worth hiring more teachers? However, we must keep thinking about our results. Another important task of the data scientist is to think about the model and its possible weaknesses. Although I have to confess that I prefer smaller classrooms.